Today I'm going to be summarizing some of the work that's been done by some of the geophysical research associates in the Metal Earth project. And I'll be starting with some work that Saeed has done recently, and he's done it with some collaborators from Smart Exploration, specifically the Technical University at Freiburg and Uppsala University. And this work was done on the Swayze East profile, that is sometimes known as Mallard Road. So the outline of the talk is that it is essentially looking at ways of processing seismic data in a crystalline environment, and there are a number of ways that can be done, and this talk will compare those ways. The standard way of processing data in a hard rock environment is a 2D pre-stack, DMO, and then a post-stack migration. And that standard way of processing the data will be compared with a 3D pre-stack time migration, and also a new technique, which is a 3D pre-stack depth migration. And the idea of this study is to find out which of these three methods gives you the best imaging results. And this is just some words that is giving a few more details for what I just said. So here we have the geology map of the Swayze area. The Swayze is up here on the northeastern part of the Abitibi greenstone belt. And if we zoom in, we can see we've got some tonalitic rocks here to the south, and then we move through mafic to intermediate rocks. There are some clastic metasedimentary rocks here, and then up in the northern part we have felsic to intermediate rocks. The seismic line twists backwards and forwards as it follows one of the logging roads, the Mallard Road, and the colors that you see here is the common midpoints and their offset distances. And the data has been processed using the two-dimensional scheme as if everything was below this thick blue line that you see here. And the 3D processing assumes that you have midpoints in the volume below this red triangle that you see here, and that allows features to be backscattered from away from that blue line and then back to the receivers on the line. So looking in detail, there is a line here, line 1004, which runs from the southwest to the northeast, and there's a cross line 1330 here. These two lines will be compared with the 2D processing in the northern part, because this line is quite close to the 2D blue line. And these two lines here, line 1008 and cross line 1162, are quite close to the blue line in the southern part. And whenever we look at the 3D data and the 2D data, we'll be looking at it from the east, as you see here with this eye that's looking from the east. So just some details about the data processing that was done to the seismic data. Steps 1 through 20 are the standard 2D processing steps that were applied to the data. And the standard processing looks at the data between 20 and 90 hertz, but these 5 to 110 hertz are where the filter has rolled off to 0. But we'll be also looking in a little bit more detail at 5 other different bandpass filters that have been applied to the data to see what information is in the other frequencies. So the other frequencies are below 20 hertz, between 20 and 30, between 30 and 40, between 60 and 70, and between 70 and 80. And also, we'll be looking at the 3D Prestack time migration with these 3 additional steps, and the 3D Prestack depth migration will have this step here, step 14-2, instead of these steps here, 14 to 20. So this is the standard 2D processing. And I've got here 6 different frequency ranges. So panel A here is the processing when we're only looking at the data that's less than 20 Hertz. And you can see in this case, the standard 2D processing doesn't really show you any strong coherent features. But as you go up in frequency, say between 20 and 30, you're starting to see some reflections down here, possibly here as well too. Going up higher in frequency between 20 and 30, these features are coming through here and here as well. And when you go up between 60 to 70 Hertz, now these features are starting to become stronger, and as well we're starting to see 2 features being resolved in here. These 2 features become more apparent when you have between 70 and 80 Hertz. And this panel here is the panel that shows all the frequencies between 20 Hertz and 90 Hertz. And this one shows those 2 features here, and shows a reflection here at shallow depths. There's a slight hint of something there, but it's not really strongly resolved at all. This reflection here is the base of the sedimentary rocks. This one here is where there is an expected interface between felsic and mafic rocks, and these 3 interfaces down here are reflections that are inside a set of mafic rocks. And the colors on the top here are just the mafic, the felsic, and the sediments as they outcrop. And just to give you a sense of what these different filters, what impact they have on the data. So if you're just looking at the frequencies less than 20 Hertz, then the wavelengths are up around 500 meters. And that means that the horizontal resolution is around a kilometer or so, and the vertical resolution is of the order of 100 meters. But as you go to higher and higher frequencies, the wavelengths start to get a lot shorter, and that means that you have a much smaller horizontal resolution and also a much smaller vertical resolution. So you expect to be able to resolve small features much better as you go up to higher and higher frequencies. Okay, so now I'm going to compare the 3D Prestack time migration on line 1004. And first of all, we're going to look at frequencies that are less than 20 Hertz. And here you can see that the 3D Prestack time migration actually has some features evident in the low frequencies. And you remember that in the standard processing, there wasn't much that was evident in the low frequencies. As you go to slightly higher frequencies, you're starting to resolve some of these features a little bit more coherently. Also, it's worth pointing out that this cross line 1330 shows mostly horizontal reflectors, and so that means that the assumption of 2D processing is probably pretty good in this particular case. This is the reflections for the 30 to 40 Hertz case here, and you can start to see they're becoming more coherent. You can see you can see reflectors 3, 4, and 5 here. And when we place the standard 2D processing in front, so this is the 2D processing here, and you can see behind it that the features are fairly similar, and these are only low frequencies, and they compare quite well with the complete 20 to 90 Hertz processing. On the right side of the profile, which is the best place to compare this line 1004, then you can see that the 2D processing doesn't see this SWE3 reflector very well, and neither does it up here on this low frequency data. So the conclusion from this is that the standard 2D processing works well for the reflectors SWE3, E4, and E5, as these are 2D structures, but SWE3 is not clear on either of the processing really. And now we're going to look at line 1008 with this Prestack time migration. And now we're looking at 1008, and we're also looking at the higher frequencies. So this is 60 to 70 Hertz. And you can see that the 3D is seeing 1, 2, 3 features in here. It's also getting some strong reflections up here. And there's some hint here of this reflector. But as we go up to higher frequencies, 70 to 80 Hertz, then we can start to see this reflector here, SWE2. And these ones are also well resolved. And this is the full range on the 3D Prestack time migration. And you can see a number of additional features that are evident in these sub-horizontal conductors, and this one is also evident here. This is strong there. And now in this one here, we're going to put the 2D processing in the front here, and you can see that the 3D is very comparable to the 2D processing. You don't really see any discontinuities across this line here, which indicates the 3D process data from the 2D process data. And this one here, you can start to see some reflections here, SWE2. But it's not that well imaged on this particular example here, which is the Prestack time migration. So there's a hint of something here, but it's not that well imaged. So now we're going to the Prestack depth migration. And we're looking at line 1004. These are all the frequencies. And you can see the 3 sub-horizontal conductors here. And on this one, you get a very strong reflection on this more steeply dipping interface out here on the right-hand side. And this is line 1008. And again, you can see these sub-horizontal conductors and the steeply dipping one here. And also you can get some strong reflections here associated with the sediments. And on the right-hand side here, we have the standard processing in front. So this reflection here isn't evident, but here it is strongly evident. So the conclusion here is that the SWE3 is imaged very well on the 3D Prestack depth migration. And also SWE1, which is this feature up here, is also very well imaged on the 3D Prestack depth migration. And these seismic results that you can see on the left-hand side have been compared with the magnetotulurks, and the magnetotulurk shows up the sediments as a highly resistive feature, and this interface is right in the middle of this highly resistive feature. These reflections, 3 through 5 that I pointed out, lie within this conductive unit down here, and this more steeply dipping interface on the seismic data shows up as a conductive feature. So the conclusions are that although most structures are visible on the standard processing or the Prestack time migration, the Prestack depth migration delivers the most complete image of all the 3 different processing methods, with all the reflective structures being inferred from this data set. And they've been imaged reliably, and they've been migrated to give sharper reflections and more coherent structures. Now I'm moving on and talking about some work done by another research associate. This is Demola Atatunji, who's been working with Gaetian Lune. And they've been working on the Timmins magnetotulurk dataset. This is a Metal Earth dataset. There were 80 magnetotulurk stations that were spread throughout the Timmins area. Many of them were along the abitibi seismic lines. The magnetotulurk data was collected between frequencies of 320 Hz and 2500 seconds, and generally the data quality is good across the region. So this is these black dots here are the magnetotulurk stations, and you can see a number of them on this western profile. There's about half the number on this eastern profile through here, and so there are some other stations further to the east in between the 2 profiles and to the west of the western profile. I just want to point out some geological features. The Porcupine-Desta deformation zone has been highlighted here in red. This is a major structure in the Timmins area with a number of past or active mines sitting just to the north of it. And there's another structure through here called the Buskagao River deformation zone, which we call the BR deformation zone or the BR fault. And there's another structure here, which is known as the Shore Dome, and there are some active and historical mines sitting within the outline of the Shore Dome. So this is the data that was processed, and it was inverted to work out what the conductivity or the resistivity structure is as a function of depth. The data that was inverted were the impedances or the impedance tensor Z, and also the tipper TZ, and this data was inverted on a supercomputer, so we didn't have to average together many of the frequencies. So we looked at 78 stations, raw data from those 78 stations. So for the impedance tensor there were 67 periods, and for the tipper there was 51 periods, and they were within the range from 320 Hz up to 1000 seconds. The inversion was tried a number of times with different starting parameters, but the optimal parameters were background resistivities of the order of 1000 ohms, and the cell sizes were typically 1 kilometer by 1 kilometer horizontally, and the vertical thicknesses of the cells started at 30 meters at surface but increased logarithmically by a factor of 1.2 for every deeper cell. So these are the results that you see here. So the first set of results are the resistivities or conductivities at about a kilometre depth, and the red features are the more conductive, the blue features are more resistive. And there's not a lot of coherency in these very shallow depths, and that's primarily because the inversion has to put a lot of conductive features in there to explain some of the static shifts that are evident in the data. When you go down to lower depths, say around 2 kilometers deep, you're starting to see a coherent conductive feature just to the north of the Porcupine-Destor Fault, which was where there are a number of historic past-producing mines. And when you get down to about 3 kilometers, this feature remains coherent through here. And you'll also notice another conductive feature up here as well too. And there is a resistive feature here that corresponds roughly to the location of the shore dome. As you get down to about 7 kilometers deep, this conductive feature labeled C4 here starts to become a lot stronger and more coherent. When you get down to about 10 kilometers depth, there it is again. It's extended and comes further down to the south. But as you go down to about 20 kilometers deep, it's shifted a little bit to the east and lies along this BR fault that I pointed out. This conductive feature that I pointed out just north of the Porcupine-Destor Fault isn't evident at 20 kilometers deep or even 10 kilometers deep, and here you can see it's starting to fade at around 7 kilometers deep. Now this is the same data, but instead of looking at plan views, we're looking at section views. So A prime is this westernmost section where you've only got about 1, 2, 3 stations. So we've only really resolved 2 conductive features. This one here is a little bit north of the Porcupine-Destor Fault. But as we get to profile C, which is this one here, we can see we've got a few more features because we're sitting a little bit closer to where the stations are. We've generally got a resistive upper crust in the top 12 or so kilometers, and below that it's conductive in what's called the mid crust. And you notice that there are a number of conductive features coming up. So this one here is a little bit north of the Porcupine-Destor deformation zone, but there are other ones here as well too. On profile D, which is here, we have again resistive upper crust and conductive mid-lower crustal conductor, and we've got a conductive zone coming up here that seems to correspond roughly with the Kidd Creek deposit, and another one coming up here which seems to coincide with Crawford. And as we go to more easterly lines, E, F, and G, we see a similar resistive feature with some conductive zones coming up through here. This one here corresponding with the Dome mine, and these two here, C5 and C6, corresponding with 2 known mines or past producers here. And this zone here, C4, is that conductive feature that runs parallel to the BR fault. So just to give you a sense of what's going on in 3 dimensions, this is that C4 conductor that I talked about here, and this is the BR fault running through here. This is the Porcupine-Destor, and you can see the conductive zone, shallow conductive zone to the north, running through some of the known deposits. This big blue zone through here corresponds roughly with the shore dome feature that I pointed out on the first slide. So these are preliminary results, and some conclusions that we can draw from this is that the magnetotulurk data shows a resistive zone, shown here in blue, in the top 10 kilometers or so. The resistivities are greater than 5,000 ohm meters, and below that there is a conductive zone where the conductivities are such that the resistivities are less than 75 ohm meters. There is a crustal stale conductor that is just to the north of the Porcupine-Desta fault and extends down to about 7 kilometers depth, and there are other subvertical low resistivity corridors that come up. You can see some of them here, and many of these locations correspond to known mineral deposits. As I said, this was preliminary results. There are plans to do a little bit more inversion, in this case inverting the MT data and the automagnetotulurk data, and doing some rigorous resolution tests to find out whether or not some of those features that I talked about are definitely implied by measurements within the data set. And also, after the final model is produced, then it will be integrated with other geological and geophysical data so as to come up with a geological interpretation of the area. And finally, I'm going to say a few words about some potential field modeling that Rajesh Vayavyur has been doing. He's a research associate in the Metal Earth project as well. And the work has been done in collaboration with these groups here: Emerson, Geosoft, Adobe, and Esri, and also Mira Geoscience, who have all provided software to assist with this particular work. So this work is intended to build on some petrophysical measurements that were taken as part of the Metal Earth project, and a compilation of those petrophysical measurements with other measurements taken by other groups in and around the Abitibi Greenstone Belt. There were a large number of measurements taken within the Abitibi Greenstone Belt, which you see here. This is the outline of the belt, and the black dots that you see on the map are density measurements, or locations where density measurements were taken, or samples were taken for measuring the density. There are about 13,000 samples where density was measured, and on this bottom map here there are about 15,000 samples where the magnetic susceptibilities were measured. We're going to look at the Jacobi traverse and see how it is these density measurements and other geophysical data can be used to help constrain an inversion. And the Jacobi area is, as you see here, there's some conglomerates through here and some mafic intermediate rocks in the area. So the idea is to work out what the density is below an interface, and the interface is between lower density rocks here, the overburden, and the higher density basement rocks. And we're really interested in the basement rocks, and we're interested in inferring their geology, and in order to infer their geology from geophysical data, we work out what their densities might be. So we have some constraints. We have a geology map, as you see here. We also have some seismic data along the Jacobi traverse, and that seismic data has been used to work out what the near surface velocity model is. And you can see that there's a low velocity layer marked in red here, and you can see the depth to the interface along the seismic traverse. This just shows the data was used to work out that low velocity model. We also have some topography data that was available from the shuttle mission, and we have the gravity data, and we also have magnetic data. So this is the geology, and this is what the basement might be. In this case it's flat, but we know what the depth of the basement is along that seismic traverse there, which runs from here to here. So that's the depth along the seismic traverse. We'd like to know what the depth is around the seismic traverse, and the information that we can use to estimate what that depth is from the magnetic data. So you can work out what the depth to the magnetic sources are. The shallowest magnetic sources will be in the basement and not in the glacial overburden. So the thickness of the overburden along the traverse and from the magnetic data is as shown here, and this is a constraint. And then we can use the geology map to work out what the geology is below the overburden, and we can use densities from the physical properties compilation to assign densities to those geological units. And then those densities can be inverted to be consistent with the gravity data. And when you do that, you find that these red units here, which are more dense, this one here stays dense, but this one gets less dense. And this yellow one, which is intermediate, gets quite low density, blue, and this blue one here, which was assigned a low density, actually gets a little bit more yellow, which is more dense. So it shows that there are some changes going on that are not as expected, particularly in this zone here where it's gone quite blue, and that might indicate that the densities are a lot less there, and that could be indicating some sort of alteration. So this is just an example of the type of information that you can extract from gravity data when you constrain the model. And this slide is just to show some other work that Rajesh has been working on. In this particular case, he took the gravity data and the magnetic data from the Sudbury area, and he did a unconstrained inversion and worked out where the dense features and the magnetic features were. And you can see that there is discontinuity in both of these features as you go from the west towards the east end of the Sudbury Basin. There's a truncation here, and then this susceptible feature picks up and continues to the east and appears to have been displaced. So there might be some sort of major fault structure coming through here that has reduced the magnetic susceptibilities in the Sudbury Basin. And there's also a potential fold structure in here as well too. So this is just a very brief summary of this particular poster that you see here that was presented at the Geo Convention in the middle of 2021.